Hello and welcome to Toddcast number 40. It just seems like that's an awful lot. Anyway, we're tying off chapter 8 at this time and the end of the reactions. And so we've gone through all the individual reactions we're going to cover. And it's a pretty large list. And hopefully you've gotten to a point where you have them all in some sort of clog chart, spider chart, whatever you want to call it, but you memorized all these. And not only you know the reagents and the product and whatever conditions and like recognize Markov-Makov, anti-Markov-Makov, anti-addition, syn addition. Most importantly, you know the mechanism well enough so that if you have a slight change, so in one reaction as you learned it, they might use water that comes in attack. So if you use an alcohol, you end up with an OR group instead of an OH group. Just recognizing little nuances of what one reagent might do. So recognizing, for instance, if we use instead of BH3, we use something else has an H on a boron and then some R group of some sort. And just have a basic idea for how reactions work in a big picture sense to look at things. Okay, that said, one of the things that's going to show up in your test for sure, explain questions, mechanism questions, predict the reagent or product question, and then synthesis. And so a big part of OChem at this point is knowing all your reactions, but knowing in the context of the types of questions. So I want to focus on synthesis. And it's a pretty major part of organic chemistry. It's probably the most important thing that organic chemists do is synthesize molecules for medicinal purposes or industrial purposes. And so it's strategically figuring out how a molecule has changed and what you can do to carry out that change. And so one of the biggest things you need to do in synthesis is strategize how to go from one structure to another structure. And one of the first places you need to start is the skeleton. So this is 1, 2, 3, 4, 5, 6 carbons, 1, 2, 3, 4, 5, 6, with a methyl on the side. So it's a methylated hexane. So I know I don't need to make any new carbon-carbon bonds. And while we haven't made too many new carbon-carbon bonds to this point, those will start becoming a bigger player in a lot of the synthesis we'll do. So for now, it's just changing functional groups. Also, conveniently, we're fairly early in our OChem travels, so the only reactions we really know to add to carbon are addition reactions to carbon-carbon double bonds or substitution reactions where we have carbon in a leaving group. So for synthesis purposes, there's probably going to be an SN1, an SN2, or an addition to a double bond involved in every one of our synthesis processes. Okay, so for this one, let's just go ahead and look at what we have. We have a bromo group on this hexane. The bromine is gone, and we replace it with two OHs, one coming out and one going in. So specifically, we've gone from a bromine leaving group to anti-hydroxyls. So we counted carbons. They're all the same number of carbons. We look at the functional groups. We notice that a BR is gone, and you have two hydroxyls. And then how they're added. Noted that one of the OH is added exactly where the BR used to be, and one is on the neighboring carbon. So the fact that they're vicinal means they're immediately next to each other, means we probably had to go through a double bond to get there. So the BR is coming off, forming a double bond perhaps, and then we're adding two OHs to it in an anti-fashion, so we got to know our reactions. So for this one, things you need to consider. Is a double bond forming in the more substituted, i.e. Zaitsev position, or the less substituted, i.e. Hoffman position? And are we adding OHs to the same side or opposite side? Are we adding two at a time or one at a time? So for this one, the regiochemistry and stereochemistry of this tell us that it must be 1,2 addition. So what that means is we add to the double bond carbon here with the leading group and the adjacent carbon. And then the stereochemistry is anti. So primary, secondary, tertiary. So in this case, the secondary and the tertiary are being added to. In this case, it's anti. So we have our terminology down. Anti, secondary, and tertiary, and we added to a double bond. Enantiomers and diastereomers, I'm not being asked for enantiomers or diastereomers in this case. But note that if this one went in front, this one went back, you probably do also have the one in back and one in front. So if I'm getting this particular stereoisomer, there's a good chance the absolute highest yield I can get would be 50% because its enantiomer will also be generated. Okay, Likely has an enantiomer. Got that. So now we need to think about what reactions we have. Do we have a reaction that generates a Zaitsev double bond? So can we go and place a double bond here, and in doing so, get rid of this bromine leaving group? So can I make that species? So we have substitution reactions, that won't do it. We have elimination reactions, and we have addition reactions. So it's not redox. I also need to mention that. It's oxidized at more than one carbon, so it can't be that. So on our checklist, we have, there we go, elimination and additions. Sorry, my computer was lagging, so I was sitting here trying to kill time for it to catch up. But we have elimination and addition, so we're going to eliminate to make this double bond and then add across. So elimination first to make the double bond, addition to react to it. So we need Zaitsev elimination, so we need a small base like NOET. So after that, we need anti-D or dihydroxylation, so we need epoxide followed by water. So let me get rid of what I did there and tell you then that I need to add, as mentioned, a small base NaOET in the presence of HOET. You're going to add a little heat to entice it to go by an elimination process. I lose my stereo center, so it's just going to be like that. And then to go from here up here, one, I need MCPBA. That's the one that forms the epoxide. And then two, I need to break it under acidic water conditions. So if I do that, I'll get my product. Sorry to click so fast. I guess you can go back and freeze it up if you want to copy it, but it works out well. So second synthesis plan, sorry about this. Again, same inventorying as before. Number of carbons, let's see, 1, 2, 3, 4, 5, 6 with a methyl, 1, 2, 3, 4, 5, 6 with a methyl. This group is being added on, so it's not really the carbon chain because it's got an O in it, but we have the same carbon backbone, same number of carbons in the backbone. It has gained an OH and an OET. So C3C2O, we're going to call it an O-ethyl, OET. It lost an H and a Br, but it lost the H over here because that's where the new group is going on. So it's kind of the same thing we just did, except now it's reacting at not the Zaitsev position, but the so-called Hoffman position. So in order to do that, I'm going to have to make sure it's a Hoffman elimination. So the Br is gone, the H is gone, the ethoxy and the hydroxy have kicked in. So it's at carbons 2 and 3, which have to be secondary and secondary. So it's a less substituted. It's anti-addition of the two. So that's going to be interesting. And it likely has an enantiomer. So again, our yield at best is going to be 50%. Not a substitution reaction because we aren't simply adding one thing for the Br. We have a second thing going on. It's oxidized at one carbon, not necessarily oxidized this carbon, not necessarily that carbon. So not a redox reaction. Elimination, then addition. Same thing we just did, except again, we now have to make sure that it is Hoffman. So we need a large base. So if I use something like LDA, again, I want to use heat. I will now have this structure. So on here, instead of where it was, CH3, I'll probably get rid of the extra carbon I decided to add there in my overzealousness. Now we need to figure out how the heck to add this. So I know epoxides carry that out, but instead of using OH or water coming in, I'm going to send ethanol in. So if I use MCPBA, and I'm only going to show one enantiomer. Reality is I could get two. So I could get this epoxide in front as I've drawn, or I could get it going in back as well. If I do my second step, where I do H plus and ethanol, then I can protonate this. It's secondary, so there's going to be no preference for which side it breaks on, which means I again also have to count on random probability that the ethanol is going to go to the carbon I want it to go to more readily than the neighboring carbon. Which means in this synthesis, I'm going to have it go there. On the backside, this is going to go up. So this is after this water has picked up the H plus. So this, I should say, oxygen has picked up the H plus. Come in, break it from the back. So in this case, my OET is coming from back. This OH is in front. So it looks pretty good for what I wanted, but I also have two issues. I had the other possible epoxide forming, and the OET could attack from either side. So I'm getting a very low yield on this one, but sometimes you live with that. Stereochemistry consequences mean you do have the risk of losing a good amount of your product to being the wrong stereoisomer or the wrong regioisomer. And so we spend a lot of effort in chemistry enticing it to react on one side or the other, so making it more stereoselective. Basically, we do what biochem does. We include an enzyme, or what we do is we have something called a chiral auxiliary, which, like an enzyme, will bind the reactant. And when it binds the reactant, it might bind it on the left side, for instance, making only the right side accessible to the next step. So we make it add exclusively to the right side. So chiral auxiliary, just want to introduce the term. If you know anything about, let's say, your stereo system, your TV, any audiovisual equipment, a lot of times you have what's called the auxiliary jack, which you can plug something in that's not normally part of the equipment and then unplug it. So auxiliary is something that can go in and come off. So a chiral auxiliary is pretty much exactly what an enzyme is in biochemistry. It adds onto the molecule, reaction occurs, and then it releases. So it's kind of like a chiral catalyst for, it's not the right word, but it's the same basic idea. So if I were to early on add some giant molecule to the front here, then the epoxide could only form in back. So I end up making it so that only one of my two possible stereoisomers occur. Then when I have the chiral auxiliary release away, I have a much more chirally pure compound. So instead of a racemic mixture of 50-50, I might have 99% of what I want and 1% of another reagent. Okay, so the concept of a chiral auxiliary is going to pop up from time to time. It's probably more in line with what you're going to do in future synthesis, certainly towards the end of this semester and the next semester. But it's a nice concept to introduce. You've already seen it with enzymes and bioclasses. Chiral auxiliaries, it's the same idea where we design something to go on, the reaction occurs, and then remove it. Enzyme binds it, substrate reacts, releases product. In our case, chiral auxiliary goes on, reaction occurs, chiral auxiliary releases. We have a relatively pure compound. So for this one, I didn't introduce that. You don't have to worry about chiral auxiliaries for this section of the class, but in time, we're going to make that just a component to consider. We are also going to, at some point, introduce something called blocking groups, where we add to one site on the molecule. So we limit the regioselectivity by binding one carbon so that the other one becomes a reactive site. So for this one, just want to introduce the concept of you can go front or back, you can go left or right. Because there's no stereoselectivity here, no regioselectivity here, I'm going to lose out and at best get 25% of this compound. So that's food for thought on this one. Probably not going to be a big deal yet, but it will turn into one of the more important topics we do. Synthesis number 3. So again, paying attention to where the substituents are, how the carbon count is, all this hopefully becomes kind of routine. So routine is, tell me about the carbon skeleton. Exact same number of carbons, a 6-membered ring with 3 more carbons attached, making a 5-membered ring. 6-membered ring with 3 more carbons attached to make a 5-membered ring. So number of carbons stay the same, so no carbon-carbon bonds need to be formed or broken. We gained a pair of CLs. We lost an OH and an H. I'm not sure where the H must have come from, but looks like we had lost an H here. lost an H here, gained an H here. So we had a net loss of one H, but also the migration of an H. So that's going to become key. We added CLs, but note that the two CLs went on at a position that was not where the OH left from. And so one of the things hopefully you've grown used to is that if there is any sort of movement of a functional group or positioning of a functional group, it probably went through something known as rearrangement. And for rearrangement, you have to go through some sort of carbocation intermediate, which means we're looking at an SN1 or an E1 in most of these cases. For this, same stories we had before, we're losing one functional group and an H and getting two functional groups. And that pretty much the only way that we know at this point to do that involves elimination to a double bond and then addition, in this case, of two CLs. So kind of getting ahead of myself, but they're my two CLs. They're anti to one another. So it likely has an antimer. Again, that's going to be the same story over and over and over. Not a substitution because we went from one functional group leaving to two functional groups being added on. We didn't oxidize at these two carbons. Highly unlikely. Do have to consider it. Elimination, then addition. Seems like it's the same story over and over. So if it's three in a row this way, then at least for this midterm, one associated with this chapter, you probably should get used to the thought that there's probably going to be some sort of elimination. You get a double bond intermediate, and then some sort of reaction to that double bond, some addition reaction. Okay, but again, the elimination we need has to account for rearrangement. So the double bond has to be between these two carbons because that is where the functional groups are being added. So I need to somehow get a double bond there. And so as is hinted at, we need to use a strong acid so it can be an E1 elimination. And again, I'm a big proponent of adding heat. So at this point, if I were to add H2SO4 without water, keep in mind that the additional water will cause hydration of the double bond. So I want to have it in the absence of water, like 98%, and I want to add heat. And in doing so, I will get this species that we just talked about. And then the CLs have to be added in an anti-fashion, which means we're going to use Cl2, and we're going to go through the chloronium ion, but we cannot have any other nucleophile there. So it cannot be CO2 with water. So it has to be an inert solvent. I'll just toss this as good as anyone. But you cannot have anything that could potentially add across the chloronium bridge. So if this chlorine goes on first, adds to this double bond right here, let's say it's in front, next one has to come from in back on the opposite carbon. But because it can go front or back, and because this can add left or right first, you're going to get in and out, but you're also going to be able to get one that's out and in the enantiomer. So in this case, the best yield I could possibly get, 50%. And just want you to hang on to that thought that whenever you have an enantiomer, you end up losing half your yield if you're going for a stereospecific product. Last synthesis. So again, have this pattern where you have to recognize how things have changed. This one, it's different than the rest. So let me do a carbon count, 6-membered ring, 1, 2, 3 other carbons, 6-membered ring, 1, 2, 3 other carbons. So surprisingly, the carbon count hasn't changed. What has happened, if you'll notice, there are 2 carbonyls. So this is one where I need to probably line it up and work backwards. So I'm going to redraw this over here. I'm going to try to get the carbonyls flush with one another so that I can make some sort of decision about what compound I have. So I'm going to put this H here. There's my O. On this side, I'm going to have this, put the H here, and I'm going to put my carbonyl here. And notice I've drawn my O in the same spot, kind of. So I don't know if that makes sense what I've done, but I've made it 1, 2, 3, 4, 5, and the O's are overlapping. The reason I've done that is because I want to point out that if I had a double bond there, then it would explain that it could be ozonolysis. So if I see 2 carbonyls, in this case paraldehydes, but just 2 carbonyls in general, and a broken ring, I know I had to break a carbon-carbon bond. So I lost an OH, check, but I also broke the ring. That's absolutely positively essential. You recognize that the ring broke, and you formed two CO bonds. Not sure where the L comes from in that, so I'll get rid of that. But you formed two carbonyls. This is one of those things that just has to cry out to you, ozonolysis. So I'm actually going to go in what's known as the retrosynthetic direction. I'm going to say that this compound that we have right here had to come from a double bond right here, because that's the only way you would have one carbon here, that's this one, and two carbons here, that would be these two. And so I now know to go in the opposite direction. I do O3, ozonolysis, and I'd have to do it in some, let's say, DMS or some sort of reducing solvent or reducing reagent, something to pick up the third O. To get from here to here, that becomes the trick. So how do you go from here, this alcohol, to this final compound? So I want it to be anti, or need to be careful, I should say I want it to be Hoffman, not Zaitsev. So when it formed in this particular location, and OH is an absolutely terrible leaving group. So this is where we have to invoke some of our reactions for being able to get a OH into a better leaving group. So this OH, I'm going to say, we can turn into like a PBr3, for instance, or treat it with PBr3, excuse me, and turn into a bromine. So that'll be one of my steps. And then I need to get Hoffman elimination, because I have to get the double bond in the less hindered location, which means my second portion of this has to be a bulky base. So I'll use LDA. And again, I like to emphasize that heat is in there to carry out the elimination reaction, preferentially over substitution. Okay, so hopefully these steps make sense. So PBr3 turned into a better leaving group, LDA to get the less hindered alkene, and then ozonolysis to get your final compound. So we know it was cleaved, so we knew it had to be ozonolysis. There's no stereochem to worry about, so we don't have to worry about like losing some to enantiomers. It's not a substitution reaction. We're not replacing the OH with some other functional group. So it has to be some sort of oxidation reaction. So elimination, and instead of elimination and addition, it's elimination then cleavage. Cleavage in this particular case was cleaving the alkene right here to form the two carbonyls. Hoffman elimination, somewhat with LDA, but we also have to make the OH or better leaving group than OH, because LDA will just deprotonate the alcohol. So first turn it into a better leaving group, then Hoffman elimination, and then finally you need a ring opening reaction, in this case only one we know, ozonolysis in conjunction with dimethyl sulfide. So these are kind of challenging. You have to get used to this. But if you start inventorying each one from the very get-go, be very systematic about how the things have changed. Carbon backbone, bonds that are formed and broken, pay attention to stereochemistry and regiochemistry, and then finally figure out what kind of reactions you have to do. But notice it was elimination addition, elimination addition, elimination addition, and then elimination ozonolysis. The synthesis we are doing in this chapter, in this unit, will be on the more simplistic side. So if you get used to that pattern, recognize what has happened, the only way that can really trick you on an exam is start making stereochem a bigger ordeal. So when you get that elimination, you have to worry about, was it E or Z? And then once you add to the E or Z, you have to worry about, do you get RR, RS, SR, SS? Worry about the stereochemistry associated with the final product. So that's going to be the next step we level it up to. But I'm going to call it a chapter right now. I'm going to be in chapter 8 with this. But note that you need to do literally 50 to 100 examples to really get this thing honed in. This is where the time you put in, the better you'll do. So be like a duck. Be cool and calm and collected above the water, but you better be pedaling like crazy below the water to get this done, because there's a lot of stuff going on. So hopefully this is all well and good for you. And this is where we will end it. And I will move on to the next chapter in the next video. So thanks for watching and see you soon. Bye.